Hello everyone, I'm Rajasri, and today's lecture I'll be teaching Snubber circuits. I'm working as assistant professor in Department of Electrical and Electronics Engineering, MLR Institute of Technology, Hyderabad. And today in this lecture I'll be discussing dV by dt production, di by dt production, Snubber circuit design and problems based on these. And here, Snubber circuits, this is especially designed in order to protect the SAR from the formation of local hotspots due to the value of rate of change of anode current, that is di by dt, near the gate to cathode junction during its turn-on process. When the thyristor is forward biased and it is turned on by a gate pulse, the conduction of anode current begins in the immediate neighborhood of gate to cathode junction. Thereafter, anode current spread over the entire gate cathode junction area. The thyristor or SAR is designed in such a way to permit the spread of current in the entire gate to cathode area. But in case if the rate of rise of anode current di by dt is more when compared to that of spread velocity of current in the junction area, in that case, there will be a chance of formation of local hotspots. Since current rises in this particular area, that is from gate to cathode junction, hotspots may be formed in that area, and this hotspot formation is harmful for the SAR and it may get damaged due to these particular local hotspots, and thereby we need to protect the SAR from the formation of these local hotspots. So, in order to protect the SAR from rate of rise of current, here we will be connecting the inductor in series. Inductor in series with the SAR such that SAR will be protected from high rate of change of current with respect to time. If this di by dt is greater when compared to that of spread velocity of electrons, in that case only the local hotspots forms. And in order to avoid this, we are making use of an inductor. We all know inductor, it does not allow any sudden changes in the current. So thereby the SAR can be protected. So that is the idea behind. And then we have dV by dt protection as well. So here SAR, it should be protected from unwanted triggering, that is high rate of voltage with respect to time, which leads to unwanted triggering. As I have already discussed this thing in my previous lectures, we need to protect the SAR from this high rate of change of voltage with respect to current. And here, whenever the switch is closed, whenever this particular switch is closed, in that case, the high amount of voltage will be appeared across the SAR. And here, SAR should not be damaged from this particular high amount of voltage. So that is the only reason here we are connecting this capacitor across the SAR so that this capacitor will be protecting the SAR. That is, when the switch is closed, high amount of voltage will be appeared across the device and this capacitor will be acting as a short circuit. So at that instant, the voltage across the capacitor voltage across this will be 0. And as the time passes, the voltage starts building across the capacitor at a slow rate. So thereby, it is in turn protecting the SAR from high dV by dt. So here, what we actually do is, we are connecting the resistor which is connected in series with the capacitor such that when the gate triggering pulse is provided and when the SAR is turned on, and if this resistor were not provided, in that case, whatever the charge stored in the capacitor will be discharging through the SAR and thereby damaging the SAR. And it should not be happen. That is the only reason why we are connecting the resistor in series with the capacitor such that the capacitor, once the SAR is turned on, the capacitor, the charge stored in this particular capacitor will be discharged through the resistance such that our SAR will not be damaged. So here There is a normal construction of the SCR, and here we need to provide the protection for this particular SCR, and for that purpose what we are doing is we are connecting the capacitor across the SCR such that this capacitor will be providing the high voltage protection. This capacitor will be providing the protection from high dV by dt. So when the capacitor is completely charged and when the SCR is turned on, it should not be discharged through the SCR. That is the only reason here we are providing the resistor such that this resistor provides the required discharge path, and thereby SCR will be protected. Or otherwise, if you see during the charging time, this particular capacitor may charge through the resistor, which increases the charge time of the capacitor. And in order to reduce the charging time of the capacitor, what we actually do is, here you all know very well, tau is equal to RC. There is a time constant, and whenever if resistance is added, in that case in turn it is increasing the time, recharge time of the capacitor. So in order to reduce this, what we are doing is we are simply connecting this particular diode across the resistor such that the charging of the capacitor will be done through the diode, then capacitor. And once the capacitor is completely charged, in that case the capacitor now discharges through this particular resistor, such that the both purpose can be achieved. That is, one is capacitor is getting charged through the diode, and other is it is discharging through the resistor, thereby protecting the SCR. So this scheme of the protection of SCR is nothing but dV by dt protection. That is protecting the SCR from high rate of change of voltage with respect to time by making use of this capacitor and complete package. And next, coming to the di by dt protection, that is protecting the SCR from high rate of change of current with respect to time. So as I have already discussed, when the rate of change of anode current with respect to time is greater when compared to that of rate of spread of electrons near the gate to cathode junction, in that case there is a chance of damage of the SCR, and here we need to protect the SCR from this high rate of change of current with respect to time. That is the only reason why we are connecting the inductor in series with that of the SCR. So here this provides the required dV by dt protection, whereas this is designed in order to provide the di by dt protection, and this is the complete Snubber circuit protection which has been provided for the SCR from both dV by dt as well as di by dt. And let us derive the formula in order to obtain each Snubber circuit parameters. That is, what should be the value of the corresponding Snubber circuit parameters that we are going to derive the formulas for each. And here what we'll do is, first initially we will assume the SCR, this particular SCR is under forward blocking mode. So in that case, without capacitance, that is case 1, we will derive considering, we are not considering the capacitor over here in this particular case 1. In that case, here let me write down the equation for the current which is flowing through the circuit. See, current will be flowing in this direction, I, current and current. Since the SCR is not conducting, it is considered as open circuit. So that is the reason current will be flowing in this direction through the circuit. So in that case, the current flowing through the circuit is given by I is equal to V by Rs into 1 minus e power minus Rs by L into T. And here let me derive this with respect to T. In that case we get di by dt is equal to V by Rs. Since 1 is constant, 0 minus e power minus Rs by L into T, and here further differentiating from chain rule, we get minus Rs by L, where T is equal to 1 because it is with respect to T. And here we get di by dt is equal to V by Rs, and here minus e power minus Rs by L into T. Here I am cancelling minus and Rs get cancelled out. In that case, we get V by L. From the above expression, we get V by L, and here since minus gets cancelled, e power minus Rs by L into T, and here di by dt at value t is equal to 0, let us obtain this. And if we substitute t is equal to 0 in the above equation, in that case we get di by dt is equal to V by L, and substituting t is equal to 0, we get e power minus 0, where e power anything is equal to e power 0 is equal to 1. In that case, di by dt is equal to, we get V by L, where we need to obtain the required value of the inductor. So our requirement is, in order to find out the formula for the inductor, where L is equal to V by di by dt. This is one of the important formulas we will be using in problems as well. And then here let us consider the voltage across the resistor, where V is equal to I into Rs. And here let me differentiate this with respect to time. We get dv by dt is equal to di by dt into Rs. And from this equation we have di by dt is equal to V by L. Let me substitute the same. In that case, my requirement is, in order to find out the suitable value of the resistance which is to be connected. So Rs is equal to L by V into dV by dt. So this is my requirement Rs. And let us consider case 2. These are the required values of inductor as well as resistance. And let us go for the case 2 with capacitance. Let us consider the circuit with capacitance. Previously, we have not considered the capacitor, whereas here in this case, we are considering the capacitance. In that case, let us see case 2, that is with capacitance. And let me write down the voltage equation. So V is equal to voltage across the resistor. It is given by V is equal to I into Rs plus, and voltage across the capacitor, it is given by the formula 1 by Cs integral I dt. We have 1 by Cs integral I dt plus, and voltage across the inductor, it is given by V is equal to L into di by dt. And now let me differentiate this particular equation with respect to T. In that case, we get, since V will be constant, we are differentiating with respect to T. So in that case, V is equal to 0, and here di by dt into Rs plus differentiating with respect to t, we get 1 by Cs, and this is since we are differentiating with respect to t, we get I, where t is equal to 1. And here L into d square I by dt square. And here applying Laplace transform to the above equation, we get here S L into S square plus S into RS plus 1 by Cs, taking I of S common, this is equal to 0. And now let me take inductor common from this particular equation. I get S square plus S into Rs by L plus 1 by LCS L into I of S is equal to 0. And now let me compare this equation with second order equation. In that case, let me consider the second order equation first, which is equal to S square plus 2 zeta omega n into S plus omega n square is equal to 0. Is it not? And now let me compare this second order equation with the above equation, and here I get 2 zeta omega n is equal to Rs by L. Yes. Whereas omega n square, comparing with the above equation, I get omega n square is equal to 1 by L into Cs. And here let me square this equation. In that case, squaring on both sides, we get 4 zeta square into omega n square is equal to Rs square by L square, where let me substitute the value of omega n square from this equation. Let me substitute the value of omega n square in this particular equation. I get 4 zeta square, where omega n square is equal to 1 by LCS, which is equal to R square divided by L square. In that case, here see L and square gets cancelled, and here I need the value of capacitance, where capacitance Cs is equal to 4 zeta square by R square into L. Rewriting this above equation, I get Cs is equal to 2 zeta by Rs whole square into L. And this is the required formula. This is the value of the capacitance which is to be connected in the circuit. And then we can also obtain the value of the resistance from this equation. We get Rs is equal to 2 zeta into under root of L by Cs. There is another formula in order to obtain the value of the resistance which is to be connected in the circuit. And then what is this zeta? Zeta, there is nothing but damping ratio, and whose value will be ranging from 0.5 to 1. And if the value of the damping ratio, if it is not given in the circuit, in that case, if it is not mentioned in the problem, in that case, simply consider zeta damping ratio value is equal to 0.65. So hereby we have derived all the required formulas, that is inductor, resistance, capacitance as well as zeta. Now let us solve a problem based on the Snubber circuit parameters. So here we have a problem, that is SCR is operated with a supply voltage of 400 volts. The dV by dt is 500 volts per microseconds, and di by dt is 20 amperes per microsecond. Calculate the value of Snubber circuit parameters and inductance for a damping ratio of 0.5. So, when a problem is given, always first try to write down the given data so that you can simply solve the problem easily. So here, SAR is operated with a supply voltage of Vs is equal to 400 volts, and here dV by dt it is given by 500 volts per microsecond, that is 10 to the power of minus 6, and here di by dt it is given as 20 amperes per microsecond, that is 10 to the power of minus 6. And now calculate the value of Snubber circuit parameters and inductance for the damping ratio of 0.5, that is damping ratio zeta is given by 0.5. And now let us firstly find out the value of the inductance, where inductance we have derived previously, where L is equal to, the formula we have got is V by di by dt, where voltage is given as 400 volts, and here di by dt it is given as 20 divided by 10 to the power of minus 6. In that case, we get the value of the inductance as 20 microhenry. Yes, similarly, let us obtain the value of the resistance, another Snubber circuit parameter. That is, let us find out the value of the resistance, whose formula is given by L by V into dV by dt, which is equal to, value of the L we have got previously as 20 microhenry. Let me substitute this in 20 into 10 to the power of minus 6, where the value of the voltage is given as 400 volts multiplied by dV by dt, it is given as 500 per microsecond. In that case, if we resolve this, we get the value of the resistance is 25 ohms. Similarly, let us find out the value of the capacitance which is to be connected across the circuit. This is given by the formula 2 zeta by Rs whole square into L. This is what we have got while deriving. So 2 into zeta, here is mentioned in the question it as 0.5 divided by Rs value, it is given as, we have got it as 25 ohms. We have got it as 25 ohms whole square into L, which is into 20 into 10 to the power of minus 6. And if we resolve this, we get the value of the capacitance as 32 nanofarad. So that is all about this problem, and in the upcoming lecture we will see BJT.